Okay, lesson 1.4, polynomial functions and rates of change. So we're going to identify turning points of a polynomial. We're going to find relative and absolute extrema. We're going to discuss relationships of extrema related to even and odd functions. And we're going to find points of inflection by using key characteristics of polynomials. So it says in this lesson, we will identify some key characteristics of polynomial functions related to rates of change. We can identify intervals over which the function is changing in specific ways. In the previous lesson, you explored the behavior of increasing, decreasing, and constant functions. And so now we have a formal definition of a polynomial function. It says a polynomial is defined as a monomial or a sum of monomials. So poly means many, so we just have many monomials here. So like we could just have a polynomial, might be like x squared, or it could be x squared plus 5x minus 7. Okay, those are both polynomials. Said to be in standard form when the terms are arranged by degree in descending numerical order. So where our largest exponent is first, and then they go in, then they just go in descending order. So they give us one. It kind of looks messy, but here is just one with a bunch of variables and everything. But all it's showing is that if you notice, you have n for your exponent, then it's n minus 1, so it's one smaller, and then it'd be n minus 2, n minus 3, all the way till we get to just x to the first, and then we have our constant that has no x there. All right, so the polynomial of degree n has a degree n, so your degree is going to be your largest exponent. So like in the little example I did up here, this would be a second degree polynomial, okay, because my largest exponent is a 2. And the leading coefficient is always the number in front of that variable that has that degree as the exponent. So in this case, we can't see it there, but it's a 1, so that 1 would be my leading coefficient. Okay, and then it tells us that a constant is a polynomial function of degree 0. Because if I have a constant function, so let's say y equals 2, it doesn't have an x there. At least it's not written. But there is an x. There's just an x to the 0 because there's no x, which that's why its degree is 0. All right, remember our turning point is where the graph of the function changes directions from either going up to down or down to up. And then the direction of the graph of a function as you move to the left and to the right away from the origin is commonly called the end behavior. So if I'm looking at like this quadratic, let me sketch one real quick here. So if I'm looking at this quadratic, what's happening way over here and over here on the left and the right, that's what we're talking about when we say end behavior. All right, so for any function f, there exists an interval from a to c that contains b, so that for all x not equal to b in the interval, then f will have a local maximum at b if the y value at b is greater than the y value of x, and f of b is called a local or a relative maximum of f. So all it's saying there is basically if we have some hilltop, or if it's an end point that's up, then we're going to have what they call either it's a local or a relative maximum of f. And then if f has a local minimum at b, then f of b would be called a relative minimum. So relative and local mean the same thing, okay? They're just two different vocabulary words that are talking about the same exact location. So when we look at this graph over here, I can see I have this little valley right here. So this is going to be my relative or my local minimum. And then I can see I have these two high points up here. So each of these high points are going to be a local or a relative maximum. And then we'll talk later about what if it is like these look like they're the same y value and they're actually the very top of the graph. So they actually have another name as well. And we'll talk about that in a little bit. All right, local maxima and minima are called local extrema of the function. The singular form is extremum. The term local can also be replaced by the term relative. So if they talk about local extrema, that's just another way of saying your local maximum and your local minimum values. All right, so A says on the graph at the right, shade the intervals of increase in green and the intervals of decrease in red. So when I look at my graph, I can see that it is increasing right here. And B is going to tell us to actually tell where those intervals are. So I'm going to go ahead and write it. So interval of increase is going to start on the far left at negative infinity, and it increases to that maximum right there of negative, where x is -1. And I can see I have another place over here where it's increasing from where that x is 2 all the way to the right, so all the way to positive infinity. So from 2 to positive infinity. And then decreasing, well, it's decreasing in between the two increasing on my graph. So right here, so it starts where x is -1, and it stops decreasing down here at that minimum value where x is 2. So from -1 to 2. Then C says label the local extrema as a maximum or a minimum. So this point down here at the bottom, we know it's a local minimum or a relative minimum. And then up here at the top, we have a maximum, which is it's local or relative. Either one. Remember, they mean the same thing. All right, example 2 says using your graphing utility, determine the relative maximum or relative minimum of the function below. State the intervals where the function is increasing or decreasing. What is the connection between relative extrema and the intervals? All right, so I'm going to put this graph into my calculator and my y equals, and I'm going to look at it. And so you may have to adjust your window some. But my graph looks like this. So I can go through and I can see I have a local maximum right here, and so I'm going to use that. I'm going to use my calculator to find that. So we're going to go to second, and the button says calc, but it's the trace button. Right above it, you'll see it says calc. And then I'm going to go find where it says maximum. And then it says left bound. So I'm going to make sure I'm on the left side of that maximum, and I'm going to hit enter. Then it's going to say right bound. So I'm going to go to the right side of that maximum. Now when you do that on either side, don't go past another turning point though, okay? So go to the right side and hit enter. We don't care about guess, so just hit enter. And so it should tell me that that maximum there is 1.458, 31.409. And then I've got this minimum value here. So I'm going to do the same thing. I'm going to go to second trace, but this time I'm after a minimum, so I'm going to choose minimum. It says left bound, so I'm going to arrow over here where I'm on the left, right bound, arrow over to the right. Don't worry about guess, so just hit enter. And it should give you the point -0.688. comma, -3.373. All right, and so now we can go through and we can answer what it's wanting us to answer. It says, what is the relative maximum? Well, your relative maximum is usually your y value, but they didn't express if they wanted as an ordered pair or just a y. So what I'm going to do is my relative maximum is going to be that 31.409. And I'm going to put at x equals, that way I covered myself as well there, the 1.458. And then what is my relative minimum? I'm going to do the same thing. So I didn't put a parenthesis there. My relative minimum is -3.373 at x equals -0.688. And then it increases. We can see that it's increasing in the middle of this graph. So it's increasing from -0.688 to 1.458. It's decreasing from negative infinity to the -0.688. And then it's going to be decreasing again from 1.458 all the way to infinity. And then the connection there is that we notice that the relative extrema are our turning points. So the maximum and the minimums are our turning points, and that's where this change is going to occur in increasing to decreasing, or vice versa. So the local extrema are our turning points. Or the change from increasing to decreasing occurs. So from increasing to decreasing, and put or vice versa here. All right, example 3. Between every two distinct real zeros of a non-constant polynomial function, there must be at least one x value that corresponds to a local maximum or local minimum value. So if we have two places here that cross the x-axis, that means there has to be somewhere in between them, there has to be a turning point in order for it to go back up or to go back down towards that x-axis. So given that equation there, A says determine the real zeros of the function. And so we can look at this graph, and it looks like they're pretty much all numbers, but we can also, I'm just going to show you real quick here, or tell you, if you go again to that second calc, which is that trace button, you'll notice, I think it's option 2, says 0, okay? So you could actually have the calculator, once you put your equation in y equals, find it for you. So when you do that, it's going to say left bound. We'll go to the left side of it, which is going to be above it. Right bound. Don't cross another 0, though. And then hit enter, forget about the guess, and it would tell you that that 0 right there is at x equals -3. And then you would just repeat it for the other two. But we can see here that this is at 0 and this one is at 4. B wants us to state the value of x where the local maximum or the local minimum occurs. So we're going to go through and we're going to find these local maximums and minimums, and then we're going to tell about their values, okay? All right, so I can see here this local maximum is at 0, 0, but I can't really tell what this one is and what that one is. So I'm going to use my calculator to find it. So I'm going to go to the second trace, and both of those are minimums, so I'm going to choose minimum. And then I'm going to find the one on the left here. So left bound, right bound, just hit enter an extra time for the guess. And it should tell you that that ordered pair there is -2.103, comma, -3.632. And then I'm going to go ahead and find this other one. So same thing, second trace minimum. Left bounds over here, right bounds over here. Hit enter again because we don't care about guess. And it should tell you that this one is 2.854, comma, -8.197. Now back to B. It says state the value of x where the local maximums or local minimums occur. So that local maximum is that x equals 0. And the local minimum, we have two of them. One of them is that x equals -2.103, and the other one was that x equals the 2.854. C says identify each local extrema value of x. of f of x. So the maximum occurs at y equals 0, and the minimums are going to occur at y equals negative 3.632 and at y equals negative 8.197. All right, absolute maximum and absolute minimum values. So it says we should note the difference between locating extreme on a graph in a region around an open interval and locating the absolute or global extreme on the graph for the entire domain. The y-coordinate is at the highest or the lowest points are called the absolute maximum and the absolute minimum respectively. All right, so if our graph has a top point that is the absolute, or they'll call it a global, one of the two, absolute or global maximum if it has a top point. If it has a very bottom point, that's going to be your absolute or your global minimum value. All right, so I see I have this graph here. It does not keep going up, so that means it has an absolute maximum. It does not keep going down, which means it has an absolute minimum. And so they kind of helped us out here in this next part because it tells us where the x value is at. But if nothing else, look here. We can see that this is the absolute maximum. And its ordered pair is 1, 3. This is the lowest point right here. So this is the absolute, or we could say global. So this is the absolute minimum. And its ordered pair is negative 3, negative 5. So then it says on the side over here, it says in the graph at the right, the absolute maximum is f of 1 equals, well, we know when x is 1, y is 3. And the absolute minimum is f of negative 3 equals, well, when x is negative 3, the y value is negative 5. And then just definition for both of them, kind of here side by side. Remember, relative or local extrema are the y values of the function where the function changes from increasing to decreasing or vice versa. And then the absolute or global extrema is the very highest or the very lowest y values on the graph of a function or on a specified domain of a function. Okay, so absolute is the highest or the lowest point of the entire graph, and relative, local, or relative or local extrema is more like you're looking for a hilltop or a valley and sometimes an endpoint, okay? So there's the difference between, remember, global is like the globe, it's the world, it's all. Same thing with absolute, that's all. So it's the highest point of all or the lowest point of all. All right, so in example 4 here, it says in the graphs below, label and identify relative and global extrema for each function. So we're just going to go through and we're going to identify these points. So I would go through and I would find their ordered pairs using that second. I just have to look at the graph. I'm sorry, they didn't give me an equation here. So I got my ordered pairs here. Now looking at this, there is no absolute or global maximum because my graph keeps going up. There is no absolute or global minimum because my graph keeps going down. So these are just going to be relative. So I have a relative or a local maximum. That's going to be 5, and it's at x equals 1. And then I have a relative or local minimum, which is going to be 1, and that's at x equals 3. And B, go through, identify your points. Oops, it's -1, -2. All right, so we have this graph does keep going down, so there is no absolute or global minimum, but I do have a local or a relative minimum. And it's going to be of -2, and it's at x equals -1. I do have local or relative maximums. The one on the left is of 0, and that's at x equals -3. And the one on the right there is at 8, and it's at x equals 2. But then because my graph does not keep going up, that highest point is also going to be my absolute or my global max. So I have an absolute max or global max at that top point, which is the y value is 8 at x equals 2. So it can be both. It's a local, but it's also the absolute. It is the very highest point on my graph. All right, C. Let's see. This one's ordered pairs, so -2, -11. Here, this one is like 3.5 and 9. So let's see, I have a valley down at -2, -11, so I have a local or relative minimum of -11 at x equals -2. I also have that local or relative maximum, and that's going to be of 9, and that's at x equals 3.5. And then, my graph does keep going down, so no absolute or global minimum. My graph does keep going up, so no absolute or global maximum. All right, and then this last one here. Identify my points. I can see I kind of have two valleys. So I have relative minimum of 0 at x equals -2. I have another one of -9, and that's at x equals +2. I have a relative or local maximum of 1 at x equals -0.8. My graph keeps going up, so there is no absolute or global maximum, but my graph does not keep going down. So I have an absolute or a global minimum at that very lowest point, which is -9, and that's at x equals 2. All right, and then we have even degree versus odd degree polynomial functions. So polynomial functions of even degree will have either a global or absolute maximum or a global or absolute minimum. So 5 says to use a graphing utility, determine the absolute or relative extrema of each function shown below. Record your answer to the nearest tenth when necessary. All right. So we're going to go through and we're going to find these maximum and minimum values rounded to the nearest tenth. So right here I got what? -0.6, -1.62. And I'm just using that second trace minimum or second trace maximum. So 0.8 and 2.1. Oops, I went too many places on that one, sorry. And then right here we have 2, 0 for that last point. And so we can see we have local minimums. At -1.6 at x equals -0.6 and 0 at x equals 2. I can also see that that first one we listed is the very lowest point. So this one here is also the global or absolute minimum as well. And then we have a local maximum. And then it's going to be 2.1, and that's at x equals 0.8. All right, the second one here, we'll go find that. It's just at 2.4. And so we have no minimums, we have no valleys, our graph keeps going down, there's no minimums. So we just have this local maximum, which is also your absolute or your global, because it is the very top point, okay? And that's going to be 4 at x equals 2. All right, then we've got odd degree polynomials. I'll go through and find those 2 points. All right, my graph keeps going up and it keeps going down, so there's no absolute or global max or min. But I have a relative maximum of 1.1 at x equals negative 0.8. And I have a relative minimum of negative 1.1 at x equals positive 0.8. And then the last one here, we can find our maximum and our minimum values. All right, my graph does keep going up and it keeps going down, so there are no global or absolute value, absolute extrema, but I do have a local minimum, a negative 3.4, and that's at x equals negative 1.6. And then have a local or relative maximum, and that's a 5.4, and that's at x equals positive 1.6. All right, and that is the end of part 1.